Okay, let's work on leetcode 1192, critical connections in a network. Here we are given n servers numbered from n to n minus 1, connected by undirected server-to-server connections, forming a network, where the connection I is just AI and BI. So this connections is a representation of all the edges of this graph, and this graph has n nodes labeled from 0 to n minus 1. So for example, this graph has 4 nodes. It's 0, 1, 2, 3, and the connections are just a list of a vector of vector. And it is asking us to find the critical connection. The critical connection is the connection. If we remove that, for example, this one, then this graph will be separated into different parts. For example, let's actually can draw something here. So if, for example, if we have a graph like this is one node, another node, another node, another one. So suppose these two are connected and all these other parts are connected, right? So if we disconnect this edge, then this graph will be separated by uh, into into two parts. Sorry, uh, into two parts, right? And this is the first part, and this is the second part. However, if you just remove this edge, then it doesn't uh, divide this graph into two parts because these parts is a circle actually, and it's because it's a circle. If you just delete one edge, the rest of them are still connected. So that is the main idea here. So this question asks us to find all the critical connections. How to do that? And the idea here we use is kind of simple. We just try to find all the uh, all the all the edges that are not critical paths. Then we delete all the edges that are not critical paths, and then the rest of them are the critical paths. For example, let's do it here. For example, we have this graph. We still draw some nodes here, and this is a node, and this is a node. We start from any node, but let's use given. Let's use this example. So, for example, we can start from any node. We just say we start from this node, and we do the DFS starting from this node. We do the DFS. Then for each node, we will label its depths. So the first node we visit will have a depth of 0. Then suppose we visited this node, then this node will have a depth 1. Then if we visit this node, it will have depth 2, right? And then if we visit this node, it will have depth 3. All of for now, everything looks normal. However, remember we're doing the DFS, so we're going to go back, right? We're going to go back. So how to change the color? Oh yeah, here. Let's change another color. We're going to go back. So in order to go back, we first, we currently at this node, then we go back to this node, right? Then we go back to this node. right? Everything looks normal. Then things are different here. So for this node, it has already visited this branch, so it should visit this branch. So it'll visit this node. Then what is the depth here? The depth here is also 2 because this one has depth 1. So this one has depth 1 plus 1 equals 2. Then for this node, it will try to visit this node, right? Because this is the left branch. It has not visited. However, this node will find that the node it will visit has a depth of 0, which is less than this node plus 1. Okay, this has some indication that we are facing a circle because it's visiting some node with a smaller depth, and smaller depth means we have visited somewhere before. So this is the main idea. In order to do this, we need to consider 2 situations for each node. So the first situation is for each node, let's write it here actually. So we randomly select a node v0, and then we do the DFS on v0. Of course, we need to remember its parent, right? And there will be 2 situations. The first situation is for each neighbor of v0, there are 2 situations. The first situation is we haven't visited v before, right? And the second situation is we have visited v before. And how to do this? So this can be known based on rank, or we say it's depth of the node. This can be known based on either you can use still use depth, or just use another state vector to remember, right? So if we haven't visited v before, what shall we do? We just DFS on v, and with v0 as parent. Then for each DFS, we require that to return some value t, and where t represent the minimum rank of this group of nodes, right? So t is the minimum rank of this group of nodes. Then we can compare the rank of v0 and rank of and t, right? And if we find t is less or equal to v0, which means we can delete edge between v and v0, because v and v0 form a circle, right? This means v and vm are in a circle. Then we can delete this edge. And the second condition is we have visited v before. Then we just get this group rank. Then compare and do the similar thing as this one. Yeah, and this is the main idea. It's not so hard, but in order to think this idea, you need to know something about rank and some distinction of how to make a return value for the DFS, right? So now let's write the code. We need to have some vector to remember which one we have visited for this one, right? So this one is visited nodes state. And we also need a vector to remember the nodes rank or just depth of nodes. And we need some vector to remember the rank or depth of nodes group. So this means for connected nodes in a circle, the minimum rank. Okay, then of course we need to have the connection for a graph. We can use a vector of an ordered set. So this is a graph. So node, this is a node and a set of connected nodes, right? Then we can do some initialization here. So st should be resized to number of nodes and false, right? And nodes should be resized to n and we say -1 because 0 has some meaning here. And for nodes, for group, I think this is still also resized to n, but the initial value doesn't matter. We just call that -1. And for this graph, we need to resize it to n. Okay, then we initialize it for all the edges in connections. We need to put it into this graph. So graph E0, insert E1, right? And by symmetry, this is E1, this is the E0. Yeah, this is done for the graph. And we also need a function to delete some edge from graph. Suppose we are going to delete edge starting from A, connecting A and B. Then we just graph A erase B and graph B erase A. For simplicity, even after this erase, graph A is empty, we just leave it there because it doesn't matter, doesn't affect our calculation. Suppose we have done this, then we just DFS from 0 and its parent is -1. And after this, we suppose all the edges that can be in some circle. For example, these edges are already deleted. So we can now just get all the residual edges and put them into the return res. So for that's graph size, and for in J in graph I. Remember it's symmetric, so we just need to get one of them, right? Yeah, this is just output 1, 3. There's no need to output 3, 1 as well. So we just need to push back I and j. No need for ji. Then we return res. Okay, then we need to implement this DFS function. This is the node and this is the parent. We say pre. Okay, so we first make a rank variable. Then if pre is not equal to -1, then we can update nodes. Nodes u will be equal to nodes pre plus 1. Okay. And for now we can update group as well. Group u will be equal to nodes u for now. Okay, and then we just for each vector for each node in graph u. So graph u is the set of all the nodes that are connected to u. So we need to do the for loop for each of those nodes, and if v is equal to its parent, we just ignore it. So for example, if we start from 0 and then go to 2, then for 2 we don't go back to 0, we go to 1, and then for 1 go to 3 or go to 0, right? Then we have two situations. The first situation is we have nodes v equals -1. So nodes equals -1 because it's initiated to -1. It means it hasn't been analyzed before. And the second situation is just not equal to -1. It means we have done something here before. If it's -1, then we can do the DFS on this node, right? So it's DFS on v with u as its parent. And if we found something interesting here, if t is less equal to group of u, then we know that because t is less or equal to group of u, we know that we need to delete this edge from u to v. And in order to do that, we need to have some variables. Minimum rank is initiated to nodes u, and we have a vector pair to remember all the edges to be deleted, because we don't want to delete those edges while inside this for loop. We want to delete them altogether after this for loop, right? Okay, and remember to update min rank with t. So this min rank is actually the minimum group rank. Okay, so because group u is equal to group to nodes u here, so you can either say group u or nodes u. Maybe we call that group u to be more clear. So in this situation, we need to add this pair uv inside edges to be deleted. Then we update min rank. Okay. Then the second situation is we have visited nodes v before, so then we can directly compare the rank, right? So if group of v is less than or equal to the current nodes. And I think this is also a current node. Yeah. Then we can put the edge inside the list to be deleted. Then we update the min rank and group of V, right? Then finally, the group U will be equal to min rank, and we will just return min rank. Okay, so this is the algorithm. Let's see if it's implemented correctly. And resize. It seems something wrong here. Let's see. So it seems all the edges are not added into the deletion. Oh, we haven't deleted, right? So for auto edges, and we need to delete edge. E0 and E first, E second. Okay, let's see. Let's see here. Let's read the program again, maybe, to see what's happening. And we can have some output, actually. For example, U and free here. And every time we have an edge, we just put it here. And we also put the output here, so we can see which one to be deleted. So we have we started from 0, and then go to 2, then go to 1, then go to 3, and go back to 0. And for now, we found we need to delete 0, 2. I think there's something wrong here, right? Because we are currently at 1, so we need to delete 0, 1 here. So this is not correct. So let's see. So let's read the program again, actually. So we have initiated the rank to be 0, and the previous one is not equal to -1. Then nodes U will be equal to nodes is pre plus 1. And then the group of U will be set as nodes U, and the minimum rank is set as the group U. This is the minimum group rank, right? And for every node connected to a graph, if V is equal to its parent, then we just continue. If we have not visited V before, T will be equal to DFS and V with its parent U. And if we found this T is less than our current nodes U, then it means this is our current depth, right? So if this T is less or equal to our current depth, it means we need to delete it. So we need to put it into the this to be deleted edge list. then we update the min rank. The min rank will always be the minimum group rank. And the other condition is if group V is less or equal to node U, then the edges will push back U and V to delete. Okay, it seems correct, but let's say where this one is coming from. So I added -1 here. So this means this one is coming from here, right? It means when we're visiting this node, it means we are going back to visit this node, right? Did we update it? Yeah, we didn't update this node, right? This should be updated to 0. Yeah, this seems correct, and let's command it these two outputs and resubmit. There's still some output. Where is oh here, right? We will command this. Okay, let's try to submit. Yeah, it worked. And the time complexity will on the order of number of nodes plus number of edge, right? And I think that's it. The main idea, let's see. The main idea is we have some depths for each node. And every time we went through the DFS process, and we will update these depths by +1 on the depths. And whenever we see a node, for example, we are at this node, its current depth is 2, and we see the next node has a lower depth compared to this one, then we know that we are going backward, right? We are visiting a node that we have been visited before. In this way, we are able to detect those circles. Then we can do other operations to remove the edges for the circle. Okay, I think that's it. Thank you very much, and see you next time.